Okay, I'd like to call the meeting to order. In case some of you don't know who I am the soon-to-be ex-president of the RASC Edmonton Centre, Tom Owen, and I'll be chairing the annual general meeting tonight. After the annual general meeting, there'll be a break. We'll have some refreshments and some membership pins to hand out to longtime members. And then we'll proceed with the regular meeting and our featured speaker. First, I'd like to acknowledge that we're on Treaty 6 territory, which is the traditional lands and gathering place of First Nation and Métis people. Next item is to approve the AGM agenda. It's up on the screen. I can't see anybody, so can I get a motion to approve it? And if you make the motion. So we're going to go to this year's awards. And I'm pleased to say that this year, the Observer of the Year award goes to Mike Noble, awarded posthumously. Mike having passed away in October. His passing was a shock to us all, if for no other reason than he was still posting observing reports on Astro in August. And here's his report from August 12th. Hi, folks. It's now 4:40 a.m. and the NLC RA is now 345 to 040, and the altitude has grown to 10 degrees. The western half of this display has gotten brighter and is quite obvious to the naked eye. There is some dim NLC in the eastern side up to 15-degree altitude, but it is a lot dimmer than the western end of this morning's 37th NLC this season. Mike Noble. He posted his first NLC observation on June 1st on Astro, and here it is. NLC number 1, June 1st, 3:45 a.m. Hi, folks. It's now 3:41, and tonight's NLC displays RA is now 320 to 100, and the highest point in altitude is 25 degrees. This is an excellent display to start the 2022 season. I'll probably go to 355 before I finish tonight's capture of this display. Mike Noble. So 37 sightings and recordings and reports in 73 nights. You do the math. Mike had previously been awarded Observer of the Year in 2015. Here's Observer of the Year award for 2022, and accepting on behalf of Mike's family will be Alistair Ling. The next award is the Franklin Lodi Award for Project of the Year. So many discoveries in astronomy these days are the products of expensive advanced technology and complicated coordination of large groups of people. Think the first image of the black hole. But science doesn't have to be that way. The awardee of the project we're recognizing this year, and I'm wondering, Abdur, if you can put the image on the screen.
Yeah, coming right up.
Oh, there we go. The awardee of the project we're recognizing this year, and you can see the image on the screen, used technology that is positively anachronistic. And he did not require collaboration on the scale of the D-Day invasion. To explain further what we were seeing and how we did it, please welcome this year's winner of the Franklin Lodi Award for Project of the Year, Richard Covey. Richard is a relatively new member, having joined in 2020, I believe. But he's now agreed to be the new Astro Imaging Cafe coordinator. He is, by the way, one hell of an astro imager. So thank you for volunteering, Richard. And I'm going to turn it over to you, and it can explain exactly what we're looking at.
Thank you. The solar can is this item here. It is caught my attention maybe a year and a half ago. And I just thought it was a really unique way to capture the sun's path across the sky from December 31st or 21st. So that would be the lowest pass. And then the highest pass I was not able to capture, but it would be on June 21st. So this is a 6-month exposure, and there's a little pinhole in this can, and inside there's a piece of photographic paper. And so it just sits there. So it's very easy to use. It's only about $15. I think it's by a man named Sam Cronwell in the UK. So we just order them online, and I actually have an extra one here tonight. So if anybody is interested in reproducing something like this, you can capture the landscape. So it's very interesting if you put it in front of something interesting, or maybe you're just your house or your street, or some people put them in ways that can capture reflections. So if anyone's interested, just approach me and I can give them this.
All right, well, why don't I give you this, your certificate, and I'll give you just a copy of my presentation as well. Thanks very much.
Thank you.
Nice to meet you. So the next award is the 2022 Bryce Hartwell Memorial Award for Excellence in Astroimaging. You know, we're lucky to have a sizable group of experienced and talented astroimagers in our club. So picking the Astro Imager of the Year award is always a difficult decision for the awards committee. However, after consultation with Abdur, and based on the frequency of submissions to Astro Imaging Corner, quality of work, and variety of subjects, the Bryce Hartwell Memorial Award for Excellence in Astroimaging goes this year to Alan Hobbs. Alan's images, come on up here, Alan. Alan's images are so well processed that they don't look like they've been processed. Abjur's just going to scroll through a few of them. Everything about the images, the color, contrast, the sharpening, the positioning, the noise, is so well balanced and well controlled that the images, to my eye, just look natural. The imager is behind the image, not in front of it, which is how it should be. Congratulations. And you wait and we'll get a little picture, I think. And hold this up. Oh, sweet. Thank you. Alan, you can take this. I'll keep it a little bit. Yeah. The next award is the George Moores Award for Excellence in Public Education. The mission of the RASC is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. So public education is central to the center's mission. From 2004 to 2019, the Northern Prairie Star Party was a fixture on the RASC Edmonton Centre calendar. Originally organized by Warren Finley, our awardees, the members of the NPSP committee, took it over in 2005 and ran it after that. However, as everyone is aware, the pandemic took hold in 2020 and resulted in the cancellation of the NPSP in 2020 and 2021. But our awardees never gave up on the idea of holding it And under their leadership, it came roaring back this year. As in years past, they put together a budget, assembled a team of volunteers, arranged camping facilities, recruited guest speakers, solicited door prizes, and set up the facilities. And this year, under clear, dark skies, there were 67 registrants, and as they reported in Stardust, quote, great camaraderie, learning, and enthusiasm. So it gives me great pleasure to announce that this year's George Moore's Memorial Award for Excellence in Public Education goes to Rick and Susan Bram. Hello. Susan, this is yours. Yeah. This is yours.
Thank you very much.
Thank you. Thank you. You may.
Thank you. We are truly honored and humbled by your recognition today. Thank you. It is quite a team effort by the two of us and involves many other people. We have had a core group of people who are in on the planning for each year to get things started.
We had, as Tom has acknowledged, and we're happy that you did, a successful kind of more or less return to normal event in 2022. And for 2022, we kind of scrambled a little bit to pull it together because we still weren't sure about things. But our organizing team, the ones that we start with at this time of year, included, and if you're here, please stand up, Warren Finley, Sharon Morsink, Luca Vanzella, Catherine Vanzella, Marion and Alan Hobbs, Kent Martins, and Chris Meerveld. And our team also includes our current treasurer, who is Florin Zabuk, and our president, Tom Owen, and vice president, Jay Lavender. So that's the group that kind of gets things started, and we're gearing up for a fantastic 2023 with the Black Nugget Lake Observatory ramping up. And so we're really looking forward to that. But at the event itself, and you talked about the numbers that showed up, and it's as you know, weather and who shows up really makes a difference for the party. And this year we had our challenges with a lot of wind with the tent. We had people coming in at all hours of the night who wanted to take part. We had a barbecue to get together. And we had, as you saw in the October Stardust, a great number of people who all worked together. And also, I know that we did have lots of people who commiserated with each other over equipment. They loaned equipment to each other. They learned new stuff. They got better images. It was really a wonderful event. So we are gearing up for this year's event. I'm doing a shameless promotion here. September 12th to the 17th, a little bit earlier in the month. And we're going to put together an organizing team with regular meetings and delegated tasks. And so if any of you who are new or would like to get on board, we would love to have you come and talk to us at the break or get in touch with us on the website. And thank you again very, very much.
Okay. Here's yours again. And here you can take, you can put it in, keep it flat. Okay. Oh. Thanks very much. Thank you. All right. Last but certainly not least, the President's Award for Service to the Center. President's Award for Service to the Center is given for sustained and valuable contributions to the center and the advancement of its mission. Our award winner joined the center in January of 2000. She was a member of the organizing committee for the 2012 RASC General Assembly, which was held in Edmonton. She has been an Edmonton RASC council member for the last 10 years, since 2013. She served as the Edmonton RASC president 2017, and 2018. She has been the RASC Meeting Speakers Committee starting around 2015 to present, inviting speakers for our monthly meetings, creating web pages, advertising the meetings, and often introducing the speakers. But that's not all. She's also a respected and popular professor of astrophysics at the University of Alberta, who has authored or co-authored to date 87 astronomy papers. So in addition to her many tangible contributions to the center, she also contributes an important intangible: credibility. And finally, may I add that having first really got to know her when we traveled down to Idaho to see the eclipse in 2017, she is one of the nicest persons you will ever meet. It is my honor to present the 2022 President's Award for Service to the Center to Dr. Sharon Morsink.
It's not true that I'm nice.
Thank you very much.
Thank you very much. And here, you can take,
Get a red folder.
you get a red folder. So just some final comments. I want to say that it's been my honor to serve as the president of this center for the last 2 years. I have every confidence in the incoming council, and in particular, our incoming president, Jay Lavender. He's going to do a great job. And I think it's appropriate that someone of Jay's experience should be taking over the helm. We're all in good hands with him and with the rest of the members of council. So all I want to say is thank you very much. I'm going to make thank you. So I'm going to exercise the chair's prerogative to adjourn the AGM. And we're going to take a break before the regular meeting commences. As I say, we have refreshments over there, and Sharon and I are going to distribute longtime membership pins. You can see the one that I finally got for 10 years of membership. And the list has been published in Stardust, but we have a list here. So if you have you been a member for more than 10 years and you haven't got a pin yet, come and see us and we'll give you a pin. All right. Thank you very much.
Okay, if we could get folks to take their seat and we maybe get the membership meeting underway. Okay, hello. Happy New Year to everyone. I will call the January 2023 members meeting call to order at, what time is it? 8:31. So just quick introduction. I'm Jay Lavender, for those of you that don't know me. I've been with the center now, I think 13 years, something like that, but there's no 13-year pin. But, I guess I get a few years to go yet for that. So yeah, Jay Lavender, new president, and I will be your RASC Edmonton Centre host for the next 734 days, 20 hours, and about 15 minutes. Give or take a few minutes. So just before we go, I think we have the agenda up there. So just a couple of things I did want to mention. I wanted to give another big thank you to Tom, who I think led us through what might very well have been the most challenging presidential term in the history of this center. So just as Tom took the seat, obviously the pandemic hit. And of course, absolutely everybody was discombobulated about that. And but Tom kept a good level head about himself and put the center, I think, first and foremost, and kept things going. So if everybody would please join me in congratulating Tom. Thank you so much for a job well done. It was rough waters there for a little bit, but wasn't too long before things were really back in the saddle. So a really good job, Tom. Well done. I would also just like to give a nod to other folks that have served on the committee, including Florin Sabak, who was our treasurer, and it's no easy job. And so Florin is stepping away from that seat, and Jeff Wheaton is now taking that role. And so I just wanted to mention, just for everybody's knowledge here, that obviously the center doesn't run itself. And I was just going through some of the numbers, and I thought I would share them with you, that to run this center, we have 16 council elected positions. We have 9 council appointed positions. We have 8 standing committees of 2 or more members, and we have 5 special committees of 2 or more members, which is about a total of 38, at minimum, 38 individuals to run this center. And so I would just like to give a big thank you out to all of those that are coming back, as well as those that have departed and given their time towards the center. So thank you very much to everybody for that. I promised Luca I wouldn't drag this out too much. So I just wanted to say I love this center. I love what the RASC stands for. I think I have quite a few new and exciting ideas over the next couple of years. I would really like to work on member benefits of being a member of the center, public education, and citizen science. I would really like to focus my efforts on those over the next couple of years. I think I have a few exciting ideas with regards to in any one of those areas. So stay tuned for that coming up. So our next, our guest speaker is Dr. Brian Martin, who's a professor emeritus in mathematics and physics at the King's University. And Brian and I have a very common interest, and we crossed paths here a little while ago. And Brian mentioned his little project that is very near and dear to my heart, and those that know me will know why. And so Brian took on a little project here on what's called the Solex spectroheliograph, and he's here to tell us how he did it. So Brian.
Thanks, Jay. Well, we're trying to figure out how to get my PowerPoint up and running. I start with an apology. By my estimation, I have missed the last 520 meetings. I was an active member of the group in the 1960s, and let my membership lapse till about 2 years ago. So I'll do better in the future. So are we ready to? Okay. There we go.
And I believe this is
My clicker. Okay, I'll probably go backwards. Anyways, thank you. Well, this is really hard to see with the light shining on you. Thank you for inviting me to speak about an amazing tool. I have to start by saying about 2 years ago, I sold my Solar Max 2, my Coronado Solar Max 2, and I was never really thoroughly happy with the images that it produced. I'd fixed it up with a nice moonlight focuser, and by the time I was finished, I'd put about $4,000 into the instrument. And I suppose it was producing to the level that Meade would say is acceptable, but I was never really totally happy with it. But I missed it. So last summer, I started to hum and haw. Should I buy a Quark? Should I buy a Lunt, which was I really wanted in the first place? And then I came across on Christian Buell's site his discussion of Solex, the Solar Explorer, and it intrigued me. So we're going to talk a little bit about an instrument that I would really encourage you to think about building for yourself if you're interested in solar observation, and especially in ultra narrow band solar observation, to put you in the same category as a quark or as a LUNT, a dedicated solar telescope. So we're going to look at sort of an adventure with a do-it-yourself spectroheliograph. And let's see, how is this supposed to work? Aha, it works. So the idea of the spectroheliograph is actually quite old. It dates back to the 1890s with the work of George Ellery Hale and Henri Deslandes, who independently developed the process of imaging the sun in a very, very narrow slice of the spectrum. You would produce that by dispersing the light using a diffraction grating, and then taking a very narrow sort of slit and scan it across the sun. So hopefully this will sort of, this is rather cheesy, I apologize, but imagine that's the slit of the spectrograph scanning across the sun. So because you can, with the spectrograph, narrow the spectral region of interest down to a fraction of an angstrom, and as you scan it across the sun, you get a thin line in a particular wavelength from which you can then build an image. Now, in the 1890s, this was all done with mechanical contrivances, and it's really quite remarkable that it even worked. 100 years later, with the use of digital imagery and high-speed computers, it's really quite a remarkable thing, and it's actually something that's very doable for an amateur. So the whole underlying principle is you use a spectrograph to isolate a very, very, very narrowly defined spectral line. Now, those of you who do narrow band filters, narrow band imaging, you're talking about a number of nanometers, or the width of your spectral region. Here, we're talking about hundreds of a nanometer. And we're then looking at the sun in very, very narrowly defined regions. So here's an example, and I'll get my laser pointer out. And I apologize, I only have one laser pointer, but I have 3 screens. So in this particular example, this is taken with the Solex, which I'll show you in a few minutes of what it looks like. So here's the magnesium triplet and the sodium doublet. So this is I used to love to do this with students to actually show them in color. The magnesium triplet is just a beautiful set of spectral lines in the green part of the spectrum. This is just sunlight. In fact, it's just sunlight pouring in through the window as I was calibrating the instrument, or collimating the instrument. This is the sodium doublet, so sort of an orangey yellow region. And this is the hydrogen alpha line. And those of you that know something about spectroscopy realize that we're talking here about a resolution of around 40,000, which is really very high resolution indeed. So you get an extremely pure red light for the H alpha, or extremely pure light if you take one of the sodium lines or the one magnesium lines. So the beauty of this is that you can just select one of these lines and scan across the sun in that wavelength, and produce then an image in the light produced by magnesium atoms or by hydrogen atoms. And there's a whole list of spectral features that you could then start to investigate with this instrument. Well, this is what it looks like. This is produced by Chaliac Instruments in France. The total cost was about 650 Canadian dollars by the time it arrived in the late spring of last year. And I was still somewhat skeptical that I was going to get great results, because it's really much less than a third of the cost of a quark, or a fifth the cost of a dedicated solar telescope. And in fact, when you think about that, I don't have to buy a quark for hydrogen alpha and a quark for hydrogen beta and a quark for calcium. I can do it all with the same instrument. It's less than a tenth of the cost of one of these instruments. It's all 3D printed. So just an ordinary entry-level 3D printer, an Ender 3. I'm sure there's some here who are very, very good at 3D printing. I'm a newbie at it. So total cost of materials was about $20 to build it, to print it. The cost from Shellyak were the optical elements. As I said, that's about $650 all told. And then I did add a helical focuser on it just to make it easier to focus the camera. Chances are many of you have some CCD cameras or CMOS cameras that would be certainly adequate to image with. This is a Neptune M camera, which is very similar to the ZWO 178. So it's a relatively inexpensive camera. So the instrument is small. There's a toonie next to it, so it gives you some concept of how big it is. It's very light. The mass is less than 700 grams. That's including the camera. And I can drive it on a very modest mount. For this instrument, I use an HEQ5 Pro, which is, as many of you who are imagers know, is a very, very low end, still a very good mount, but certainly not a very sophisticated mount. So it's an instrument that is very low cost and is really quite easy to produce. The only bad news is it's not an optical instrument in terms of, or it's not a visual instrument. You don't look through it. And that might be a turnoff for some of you. But when you see the image being built on the computer screen, it's pretty exciting. It's actually quite addictive. Just to give you an idea of how you operate it, this is just a simple dial that you can use to rotate the grating. So if you want to look in the red end of the spectrum, hydrogen alpha, you just rotate that into the field of view on the camera. If you want to look in H beta, you just rotate it and so on. So you can select the spectral region that you're interested in imaging in. Oh, that's, if I was thinking, see, most of you are over there. Yes. Okay. Well, this one over here. That's the best one. Okay. That's a good idea. So this is basically what you're looking at when you purchase the kit. You get a couple of doublet lenses that you use for the imaging camera lens and the collimator lens, and a holographic diffraction grating and a thin slit. The optical layout is a very simple, it's called a classical spectrograph design. The slit of the spectrograph is right here, and this is what the telescope is focusing the image of the sun onto that slit. It's right at the focal point of the collimating lens, so it produces a parallel image. You're basically running a slide projector at this point. It produces a parallel image of the slit, and then that hits the dispersing grating, and the grating then disperses the light, and you get multiple images then of the slit in all different colors projected onto your camera. Okay, so that's the simplicity of it. So this is an idea that is more than 130 years old, but today it's something that we can do quite nicely at home. I'm using a 2400 line per millimeter holographic grating. So again, that's a very, very densely packed grating. And this particular setup is optimized for a small telescope. It's optimized for about a 400 millimeter focal length telescope. And, that would be something like a 60 to an 80 millimeter diameter telescope, somewhere f6 to f8, somewhere in there, in that regime. So that's again a relatively inexpensive telescope that you would be using this on. So I'll show you a sample run of what it looks like when we scan across the sun. This will be a hydrogen alpha scan. It's imaged with a stellar view SV70, so it's at 420 millimeter focal length. It produces a full image of the sun. In this particular case, I'm using a Neptune camera, and I'm running it at 375 frames per second. So if any of you are doing lucky imaging, then you might say that's a fairly high frame rate. So you would you would need to have a computer with probably a solid state drive, which they're becoming very, very affordable. So there's nothing exotic here. So I'm using an Asus laptop with a solid state drive, and I can easily run this thing at 375 frames per second. And the scan, pardon me, took about 8 seconds. And what I'm doing is I'm imaging the sun, making sure I'm focused, and then I'm just scanning upward and downward in deck. So I'm just scanning across the surface of the sun in declination, and I have the slit now sort of aligned perpendicular to the direction in which I'm scanning. So I just basically, just like that opening graphic, I'm able to just scan the slit all the way across the disk of the sun. And it takes about 8 seconds to produce an image. So I'll try to run the video here with the mouse. Okay, let's try this. There we go. So you'll see here's hydrogen alpha. And now we'll see it scanning across the sun. And here's the image of the sun starting to appear. So we're taking about 4,000 frames, 4,000 little slices in that very, very pure spectral region of hydrogen alpha, and then stitching them all together in the software to produce an image where you can see really quite beautifully the filaments on the sun, prominences, sunspot region. You see lots of plages there. The sun was fairly active that day. The opening image I colored just for aesthetic reasons, but let me see if I can just back this up a bit now, because I would like to just show you a few things on the, can I do it this way? Yeah, okay, I think I can. There we go. I'll just leave it like that. If you look carefully at the spectral line here, this is again hydrogen alpha. This is getting towards the edge of the sun. So this is the limb of the sun. So you can see light spilling over here. It could easily be a prominence that we're seeing. But you'll notice that the spectral line is not sharp. Spectral line is quite wavy. And that's called the Doppler-Fizeau effect. And it's really the fact that the gas on the surface of the sun is churning, it's bubbling, some of it is moving upward towards us, and that causes the light being emitted, in this case by hydrogen atoms, to be blue shifted. So it causes the spectral line just to shift a little bit to the blue part of the spectrum. And similarly, patches of gas, in this case in the photosphere, or in the chromosphere, that are descending will be red shifted. And depending on how fast they're going, they'll be red shifted or blue shifted by varying amounts. And it produces this characteristic sort of fuzzy line. When you see that, you know you're well focused. You're getting very, very sharp focus, and you're getting really, really good sort of spectral resolution. We get a resolution of less than 1/10 of an angstrom with this instrument, which is why we can see things like the filaments and the prominences so clearly. So that's, if I just hit the go button again, we'll see it continue. You'll notice it's the kind of an oblate spheroid shape. That's telling me I have a slight problem in my setup. I probably am sampling a little bit too fast. I probably should slow my scan rate down to about 10 seconds. And it was also tilted a little bit. And that just tells me the slit was not exactly perpendicular to the direction of scan. It was off by a couple of degrees. The software can compensate for that. That wasn't too bad. But if I really want to get the most out of the instrument, I should probably tune it. But I think you'll agree that that's a pretty remarkable image for just one scan. And you can do a series of scans, and then you can add them together and do some averaging. Okay. So in this particular case, it's with the camera that I'm using, I end up with a resolution of about 40,000 and a spectral purity of around, well, 0.7 of an angstrom, 0.07 of an angstrom, which is certainly much better than you could do with a Coronado or a Lunt, and probably is better than what you would do with a quark. So here's a couple of images and comparisons. This is taken with the Solex this past summer, sometime in July or August. And this was taken a year or two earlier when I still had my Solar Max 2, which had a double stacked solar. It was it ended up being an expensive instrument. And I would suggest that that is a superior image. There's certainly a lot more detail being shown there with the filaments. Here we're seeing some prominences. When we see the prominences face on the sun, they're in shadow. We call them filaments, and occasionally you'll see them spilling over the edge. We call them filiproms when you can see them emerging from the surface of the sun. It's really quite remarkable. So here's a $650 instrument compared to a $4,000 instrument. I'll let you be the judge of what you think is producing a better image. And this, I might add, is one of my first images with the camera, with the Solex. Yeah, they've gotten better since then. So let's look at a couple of other examples. Here's now moving from a 400 millimeter focal length to a 700 millimeter focal length. Now the problem is that camera was never, that spectroheliograph was never designed for that long a focal length. So you can't get the entire image of the sun in one shot. So I can get a slice of the sun. So again, comparing it, this is the Coronado, now using a Barlow lens to, effectively increase my focal length to about 700 millimeters. And this is with the Solex. And I think there's no question that this is a superior image. Nice sort of hedgerow prominence here on the Coronado. One issue I always had with the Coronado was I could never get uniform illumination across the entire solar disk. Maybe it was just me, but I tried tweaking it every which way. Under good conditions, that's not an issue at all with this instrument, with the Solex. And again, the color there is simply just added for aesthetic purposes. So that's imaging in hydrogen alpha. These are not great images. I just took typical images. The one drawback I should add too is that after an imaging session, you have accumulated probably on the order of 100 to 200 gigabytes of data, because each scan is roughly, 4,000 to 5,000 frames. So each scan is on the order of, 15 to 20 gigabytes. And it's a pretty easy way to kill time. It's a good thing I'm retired, because I can just sit there running it over and over. And I have to admit, I had fun. So this is not a really good image. This is just, I pulled one out of the junk drawer. That's an artifact. And there's a little bit of artifacting there. That was when the mount stalled a little bit as I was doing a scan. Every once in a while in the deck, it was something perhaps on the worm gear, it would just stall for even just for a tenth of a second. You could actually see it stall. And that's going to, of course, is in a sense, ruin your image. Fortunately, it occurred right there. Very, very easy to detect prominences with this instrument. This is simply a mask that's produced in software. And if your exposure is just right, it's quite easy then to see the prominences standing out quite clearly on the limb of the sun. But this is by no means a great image with this instrument. I've certainly taken much better images of that. If we blew up the image a little bit, you could see some raggedness, and that's turbulence in the atmosphere. So you're unlike what you can do with lucky imaging, where you can take thousands of images and then sort of filter out the bad ones due to turbulence. You really can't do that here. You're trying to scan as quickly as possible so that if you hit one of those moments of a few seconds of really, really good seeing, you won't get turbulence, and that won't distort the image. But I'll show you some images in a second. I think you'll agree that it works. You will find those nice moments of quiet in the atmosphere. This is calcium, K-line. In fact, the very first image taken with a spectroheliograph, I think it was in 1892. That was George Ellery Hale, and he did it in calcium. simply because in 1892, the photographic plates that he was using were only really sensitive in the blue part of the spectrum. But this was taken this summer in August with the Solex tuned into the calcium K line. Focus is a little bit soft there, but still, I didn't have to go out and buy another quark or another Lunt telescope dedicated to that wavelength region. I just turned a little red knob. So let's keep on going. I don't know if you can see the colors there. Can you see the red and the sort of orangey and blue colors? One of the beauties of this thing is now, because I have that spectral line in the software, I can tune off the center of the line and I can look at a little bit on the red side of the line or a little bit on the blue side of the line. What I'm then looking at is actually motion in the sun. I'm looking at red shifts and blue shifts and put them all together. And you'll notice there's a distinct bluish tinge on this side of the sun and a reddish tinge on that side of the sun. Well, guess what? You just measured rotation of the sun. You're seeing part of the solar disk that's moving away from you, that's being red shifted slightly, part that's moving towards you, being blue shifted. Okay? But if we take now this region right here where there's some sunspots and zoom in, now we can start to get a picture of the dynamics around the sunspot. We can see that there are plumes of gas flowing into the sunspot away from us. So they're being red shifted, and then there's material moving outward, blue shifted. So you can start to do things like looking at velocity profiles on the surface of the sun. There's a lot of things you can do with this little instrument. Now, I wish I could say that was my image, but Doug Smith in London, UK, a friend in London, UK, has been doing this for many years. And I will show you a picture of his spectroheliograph in just a few minutes. He's produced this past summer some outstanding images. If you remember, London and all of the British Isles were in this enormous heat wave in the summer. So he would image early in the morning as soon as the sun was in a good enough position, but he just produced some absolutely amazing images. He's using a 720 millimeter focal length. I am using actually one of Doug's slits. Doug, several years ago, had larger slits made, so I'm not using the spectrographic slit that came with the Solex. I replaced it with a bigger slit, about a 12 meter long slit. So that is really optimized for a 7 to 8 or 900 millimeter focal length telescope. To get an idea of the size of the image on your spectrograph, just divide your focal length by 100. And that's going to be roughly how big your image will be in millimeters. So my slit now is 12 millimeters long. I'll be imaging with 700 millimeters in the next version of the spectroheliograph. And that's the sort of the level of detail that I'm looking for. But here's one of Doug's images in H alpha. Let's look at a couple more. This is a blow up of one of those. Now, I think that's quark level, or maybe even beyond quark level. Again, now when you look at Doug's setup, you'll realize that that's got to be less than a tenth of the price of something like a quark. I know I sound like a salesman, but I just really think these are, I just hope some of you will be enthused enough to get involved in this. So just look at the detail around the sunspot. You get this sort of vortex that already in 1890s Hale was talking about observing. Some beautiful wispy prominences. And here's a philoprom. You really start to almost get a three-dimensional impression of what's happening on the solar surface. So that's just a beautiful image taken in hydrogen alpha. Here's an image now taken in hydrogen beta. So further into the blue part of the spectrum. And you start to see different characteristics on the surface of the sun, or actually in the chromosphere, because you're now looking actually at different heights in the chromosphere that favor the emission of particular atoms or particular states of ionization of atoms. And in this particular case, we're looking at light being emitted by hydrogen in the hydrogen Balmer line. but you can still see faintly prominences on the edge of the sun and some filaments. Here we have the calcium H line. The calcium H and K lines are two lines that are very, very close together, far in the violet part of the spectrum. And when you image in those wavelengths, again, the sun presents yet another face, a different face. The amount of science that's here is truly remarkable. And an awful lot of what we know about our stars, because we've been able over the last century to image it in all these different wavelengths. And finally now, in the last decade, amateur astronomers can start to take part in this process of investigating the sun. That's Doug's setup. It looks pretty hokey, but he knows what he's doing. So again, he's using an HEQ5 as well. So there's not a huge cash outlay in equipment here. He's making use of just sort of surplus lenses. I mean, how many of you have old 35mm camera lenses laying around? I suspect a few of you. If not, they're very, very inexpensive to buy now. So for a matter of $50, you can buy what used to be a $700 or $800 lens, and they are actually considerably better than what you would get in the Solex kit. But that's not to say the Solex kit isn't excellent. It is very good. But this is Doug's setup. This is, instead of 3D printed, he put it on foam board. So he's using Gator board, and those of you who know something about modeling and things like that know that Gator board is very stiff. So it's actually a very rigid material and very, very light. So his approach was to build it differently, but I think that his results speak for themselves. So this is the version that I'm working on right now. And these are just a couple of surplus Pentax Super Takamar lenses, 150mm lenses. There'll be a 50mm diffraction grating that will go there. And this is just a rotating disc. So I can, again, just turn the diffraction grating to center a different spectral line. It's 3D printed. These are just strips of double-sided tape. I've just dry assembled it to make sure everything's going to fit before I start drilling holes. And then I'm going to clad it with Gator board as well. And that's more for temperature stability, to give it a little bit more insulation, so that in the heat of the day, when you're looking at the sun, it's not warming up and causing some shifting to occur in the elements. But again, the total mass of this camera will come in at less than 1,500 grams. And that's with the camera, the imaging camera, the Neptune or the ZW-0178, and the two lenses, which are considerably more substantial than what you would get in a Solex kit. This is the collimator assembly. So the slit lives here, and you just collimate the lens. You're sending a parallel beam out to an image of the slit, and then dispersing it and focusing it down here on the camera. So in principle, it's a very, very simple device. And I think you can see that it's not you don't need an elaborate machine shop to produce this. I suspect that quite a number of you have 3D printers or access to one. I think, Jay, we talked about, when we spoke about the idea, maybe the center should have a 3D printer for members to access. But this is a technology that's readily available now. I had to kind of, as an aside, several years ago, I sold my little metal lathe because all I was doing was turning plastic parts on it. And I bought a 3D printer. And I've gotten an awful lot more use out of the 3D printer than I ever got out of the little metal lathe. So it was a good transition for me. So that's sort of what we're looking at with this instrument. Just to close, and then if you want to have some questions or discussion, that would be fine. Couple of books I could recommend if you're at all interested in this. Ken Harrison is a real leader in the sort of the pro-am connection here with amateurs and professionals collaborating spectroscopically. He's written a couple of very, very useful books, Astronomical Spectroscopy and Digital Imaging, or Imaging Using a Spectroheliograph. So they're both books that I would recommend, certainly well worth reading. And then finally, the solar chat forum for the Solex group. There's several hundred members of the group now worldwide building these cameras, and an extremely useful chat group to be a member of. And if you're at all interested in building one of these things, I would sort of encourage you to check that out. You can now buy from Shellyak an entire kit where the parts have already been printed for you. I don't know what the cost is. It's probably going to cost you somewhere in the order of $800 or $900 Canadian. You know, that will save you the frustration of 3D printing, but 3D printing also gives you a skill that as an amateur astronomer, especially if you're doing imaging and things, you every once in a while need a little adapter. If you can just print it, that's awfully nice. But if you don't want to go that route, but you're interested in perhaps building one of these, they're very simple to build. You know, the learning curve to get the first good set of images out of them is fairly steep. It's not like you just go out there and plug and play. But after a few days of tinkering with it, you finally hit that sweet spot. It's a little bit like riding a bicycle. You now know how to do it, and you're up and running. Okay, so I'd really encourage you to think serious about this as a project if you're at all interested in solar observing. So that's my dog and pony show. Are there any questions, or did I convince anybody to try doing this? Jay or Conway and preaching to the choir. Yeah, I think it would be great if we could get a group of people together and build a few of these, or even build one. It's but I do warn you, you can waste an awful lot of time on an afternoon when you should be mowing the lawn. Just saying.
The resolution is dependent on the width of the slit, not the size of the sensor.
Right. Well, no, let's back up. The slit width will determine part of what your spectral resolution is going to be. The pixel pitch on the sensor will also play a role there. In the case of a 178 camera, it's I think 2.4 micron. The slit is, it's nominally it's 10 microns, but you're looking at it at such an oblique angle that it's actually more like 3 or 4 microns. So it's a very, very thin slit. I wouldn't really recommend this for looking at stars. Although Solex comes with a little adapter, you can turn it into a stellar spectrograph. I think you're going to get so little light throughput that about the only thing you could look at is maybe Sirius or Capella. Okay, unless you went to a much lower dispersion diffraction rate, which is the next thing, of course. I'm using a 2400 line per millimeter grading. So it disperses the light way out. So if you went to a 300 line per millimeter grading, then you would have a much more compact spectrum at a lower resolution. Yeah, but that's a good question, and there's a number of factors that determine that. That's different than the resolution from the point of view of sharpness of image. And that's very much dependent on the atmospheric conditions. And that shows up by creating a fairly jagged looking, especially in the limb of the sun, instead of it being sharp, you see it jagged. That's telling you the seeing is not particularly good. And that degrades then your image a little bit. But by stacking maybe a dozen of those images, you can sort of get back some of the benefits of things like lucky imaging, where you can do a little bit of averaging of that noise out. Good. Okay. So,
Thanks again very much, Mike. Appreciate that. And I'm happy to say that I just finished all my 3D printing. So I'm about to go through the assembly process. And if 2 left thumbs lavender can do it, anybody can do it. So I'll keep everybody updated on that. But as Brian alluded to, that's something that maybe in the future we will do some workshops around. on maybe assembling the Solex or building and assembling and maybe using it. So stay tuned for that in the near future. Okay. So now we'll move to the next segment here where I know Abdur is going to do his astro imaging corner number, I believe it's 125. And I think he's got a pretty interesting compilation for us today.
Awesome. Thanks, Jay. Okay, I am ready to go when you are. Okay, let's move this out of the way. Okay, so thank you very much for joining, everyone. And as Jay said, this is Astro Imaging Corner number 125. And if you're having trouble hearing my audio or you can't see my screen, just send me a message or just let me know. So since this is kind of closing out the 2022 year, we're going to have a special edition today. So instead of showing the images that everyone had sent in, I am instead going to share some of the notable submissions from the last year. So I decided to pick one submission from everyone who submitted some images in 2022 and share those and share what I liked about that particular image or why I picked it. And if you had submitted some images this week, since that's in 2023, those will not be included as part of this submission. So let's get started. And for anyone who might be joining us for the first time, this is the segment where I share any images that have been sent in by members. So I'm just going to make this full screen. And for anyone who might be wanting to send in images for future meetings, you can go to our website at the RASC Edmonton homepage. And at the bottom left, you'll see a link for emailing Astro Imaging Corner. So just click on that link, add your images and send them over. And I will add them to the next month's meeting. So the first image that we have received, so this is one that I picked for Ray. This is the Heart and Soul Nebula. And I've followed Ray's images for several years now, and just the improvement I see every single time he sends in some images is quite enormous. And yeah, this is one of my favorite images from Ray. And this one was taken with the ASCAR 300 millimeter lens with a QHY 367 full frame camera. And for anyone who has tried to image the Heart and Soul Nebula, you'll know that it's a fairly tough target. It's fairly faint and very, very large. So not an easy target to image, but the processing and composition and everything is on point in this image. And this was taken at the Northern Prairie Star Party. So great job, Ray. And up next, this is an image from Mark, and this is the NLC that Mark had imaged from Holy Cross Cemetery in Edmonton. And this was in the summer of 2022, early July. And again, beautiful image, and you can see the NLC clouds at the very back there being lit up by the setting sun. And up next, this is the image that I picked from Arnold. And this is an image of the sun in the calcium line. And this was taken as part of the RASC's collaboration with NASA ESO and the AVSO Solar Orbiter. And this campaign was organized by Jay Lavender, and the members had submitted some very good images for that. So again, thank you, Arnold. And up next was an image from David Fielder, and this is the Heart Nebula IC1805. And David had taken this with the Celestron Edge HD8 with Hyperstar, and this was a total of about 18.5 hours of exposures, and it was taken from a Portal 8 sky and processed entirely in PixInsight. So a beautiful job there with the colors, David. Awesome. And the image I had picked for Tom was this image of Messier 94. And this is a galaxy in Canis Venestici, about 16 million light years away. And the reason I picked this was I absolutely love the processing and especially that inner ring structure with all that star formation going on that you can see. So not an easy target to process just because of how much brighter the core area is compared to the faint outer regions. But Tom did a great job and was able to highlight both the core as well as the fainter outer details. And this was taken in April 2022 from Pigeon Lake. And Tom was using his AGHD at f7 and a QSI 683 camera. And this was a total of about 2 hours of exposures in LRGB. And again, this one was processed in Star Tools and stacked in APP. So great job there, Tom. And this is an image sent in by Warren Finlay, and this is a nightscape from southern Idaho. And this is actually just a single 40-second capture with no tracking and all natural light taken in September 2022. And the moon was near the setting, but hadn't quite set yet, and that allowed the moonlight to light the foreground. And to block the glare of the moon, Warren had taken a shot in the shadow of the trunk of the juniper tree at the right. So as always, Warren, I love your compositions, so great job there. Up next is an image from Alistair Ling, and Alistair is known for his amazing compositions. So I selected this image as kind of representative of the kind of work I love seeing from Alistair. And this is the moon rising over downtown Edmonton. And this is from April 17, 2022. And this is a composite of 4 images at 200 millimeter focal length, all at 1/5 of a second. So again, beautiful shot. This next image is from Murray Paulson, and this is Messier 22, a large globular cluster, and one of my favorites personally. And this was taken with the William Optics GT71 and a field flattener. And Murray was using a Canon ATD at ISO 1600. And this was processed in Deep Sky Stacker, and some mild adjustments were made in Corel Paint Shop Pro. And this was actually taken from Mount Cobal. So again, very nice star colors. This next image was sent in by Craig Sherris, and this is the Iris Nebula. And this is from October 2022, and it was a total of about 12 hours and 45 minutes of exposures using Craig's 120 ED Skywatcher refractor and an ASI 2600 MC camera. And Craig had done a great job highlighting that faint outer dust around the reflection nebula itself, as well as the very nice blue color in the core. So again, great job there. And up next is an image from Yusuf Hussain. And this is the Lion Nebula, which is a hydrogen alpha region in the constellation of Cepheus. And this was photographed from Yusuf's backyard in May and June 2022. And due to the time of the year, the image was solely narrow band since it was summer and the sky is quite bright. And Yusuf used the HOO blending method since he only got data in hydrogen alpha and O3. And he hopes to image using the sulfur filter in the future as well. Silicone, and then try another blending method. And this was a total of about 4 hours of H alpha data and about 2.5 hours of oxygen data for a total of 6.5 hours of integration time. And again, the equipment used here was a Skywatcher ED120 and the ASI 6200mm full frame camera. So again, beautiful job and very nice processing there. The next image is this beautiful shot of the sun in hydrogen alpha from Brian Martin. And again, shows exquisite detail in the outer regions, those prominences just leaping off the surface, and very nice color and processing as well. So thank you for sending that in. And this was taken with the Solex spectroheliograph. And it looks like my Coronado PSD is now up for sale. The next image is from Alan Hobbs. This is the Horsehead Nebula, and this also demonstrates why Alan won the Astro Imaging Award for this year. Absolutely phenomenal processing, and just the colors are very, very nice. And this is a very tough target, as anyone who has tried imaging the Horsehead Nebula would know. The bright star Alnitak right above the Flame Nebula there is very, very hard to tame. So amazing image. And this was taken at Casitas Tequila Guest House in New Mexico near Silver City on March 27, 2022. And this is a total of 41 minutes of exposures. And it was taken with the Celestron RASC 8 and the ASI 2600 MC Pro camera and processed in PixInsight and Photoshop. And this next one is from Josephine. However, I can't play the video here, so I have it open in the background. Just gonna switch to that because I really wanted to show this video today. And as you can see, this is the Northern Lights from Josephine's webcam. It's amazing what you can do with a webcam camera these days, and you can see the Northern Lights dancing even from just the suburbs. So again, beautiful job, and thanks for sending that in, Josephine. Oh, it looks like it closed me off. I will, oh, there we go. Okay, next image is from Rick Bram, and this is the lunar occultation of Mars. And this was taken about 1 minute before occultation. And Rick was using his Canon 5D Mark IV on a tripod with a Canon 300mm f4 lens and a 2x telephoto extender. And this was processed in Photoshop, and Rick used 1/2500th of a second exposure to freeze the action. So again, great job. This next image was sent in by Susan Bram, and this is, you can see the sun dogs around the sun there. And Susan took this while they were driving to Calgary, and there were passengers, so they weren't taking pictures and driving at the same time. And this was on the afternoon of, well, basically late 2021, early 2022, and Susan took this using her iPhone. And the next image is from Dave Mussel. This is the Pelican Nebula, and this might be one of the best examples of this object I've ever seen. An object like this is always a tough target when it has so much dark nebulosity in there, because it's very easy to end up darkening some of those regions too much or keeping them too bright and introducing noise. But the processing here was absolutely masterful, and you can see an immense amount of faint detail in there. So again, great job there, Dave. And the Pelican Nebula, for anyone who doesn't recognize it, is located in the constellation of Cygnus, right next to the North America Nebula. And this image was a total of 6 hours and 20 minutes of data captured over several nights in August. And this was with Dave's Explore Scientific refractor, a 5-inch refractor, I believe, with the QHY 268M camera. And this was shot through HA03 and S2 filters, and it was processed in PixInsight and Topaz Denoise AI. And the next image, I chose this one from Denis. This is the Tadpole Nebula. And this was taken at BNLO, the Black Nugget Lake Observatory, during the star party there in September. And this was with the William Optics 132 refractor using an L Extreme filter on a Celestron CGX mount. And this is a total of 49 3-minute exposure, so almost 3 hours of exposure time, and processed in PixInsight and Corel Paint Pro. And you can see the tadpoles right near the center of this picture. Those are the two bright heads there with the tails. So again, beautiful job and very nice processing. And up next, we've got the image from Al, and this is the southwest terminator of the moon that was taken with a 10-inch f6 Dob and a 2x power mate. And this was taken through a Teleview 27mm panoptic eyepiece using eyepiece projection with a Canon R6 DSLR. And Al had gotten 2 to 3 minutes of video and processed it in PIPP, AutoStacker, Registax, and Photoshop. So very nice detail there. And the last image here is one of mine. So I had submitted this image of the Crescent Nebula, and the Crescent Nebula is about 5,000 light years away from Earth, and it was created when the fast-moving stellar winds from the star in the center of the nebula collided with some slower moving material that was ejected by that star a few 100,000 years earlier. And this was with my Celestron C11 at GHD and Hyperstar using my ASI 1600 mm monochrome camera and a filter wheel. And this was a total of almost 22 hours of total exposures. And yeah, pretty happy with how that turned out. And that is it for tonight. So I'm going to send it back over to Jay, but I just want to say thank you to everyone who sent in images this year. And I look forward to seeing a lot more from you all in 2023. So back to you, Jay.
Okay, thanks very much, Abdur. Honestly, the creativity and the skill is just second to none. So that's really impressive stuff. Okay, we're in the end run here now. So just before I make a couple of announcements, I thought I saw Mark Zelchuk. Is Mark here? I saw you had a book in hand. Did you want to speak about from our library?
Good evening. Yeah, the Lamplighter Memorial Library is just off the entrance to the Star Theater here. Book of the month for this month is The Consequential Frontier by Peter Ward. I'll just read what it says at the back. The Earth is in trouble so dramatically that we're now scrambling to explore space for valuable resources and a home for permanent colonization. With the era of NASA's dominance now behind us, the private sector is winning this new space race. But if humans and their private wealth have made such a mess of Earth, who can we say won't do the same in space? In The Consequential Frontier, technology journalist Peter Ward raises this vital question before it's too late. Interviewing tech CEOs, inventors, scientists, lobbyists, politicians, and future civilian astronauts, Ward sheds light on a whole industry beyond headline-grabbing rocket billionaires like Jeff Bezos and Elon Musk, and introduces a new generation of activists trying to keep it from rushing recklessly into the cosmos. With optimism for what humans might accomplish in space, if we could leave our tendency towards deregulation, inequality, and environmental destruction behind, Ward shows just how much cooperation it will take to protect our universal resource and how beneficial it could be for all of us. So this book is available after the meeting. Thank you very much.
Okay, thank you, Mark. So just a couple of notes on upcoming events. So this Wednesday, 7:30, it'll be on Zoom. I believe the link is on the website, is the Observers meeting hosted by our own John Stolte. So if you have any projects underway or done any recent observing events, please feel free to participate in that meeting. January 18th is the Astro Cafe, How to Use a Telescope. Again, one of the more beneficial to the public events that we put on, usually very well attended. So that's coming up January 18th. It's just Zoom, is that right, Luca? Or is it also at the community hall? It'll all be on Zoom, okay. What's up over Edmonton? I would say this is one of the most underrated things that we do. Jeff, it's Jeff, and it's great. So it's really good information about what's up over Edmonton, usually for a month. And Jeff makes it very entertaining and very informative. So it's well worth your time to attend. And again, that's on Zoom. And also coming up on Wednesday, February 8th is the Astro Cafe, which is the astronomy swap meet. So that's an equipment swap meet. Again, that will be occurring at Windsor Park Community League. And again, do you want folks just to get a hold of you, Luca? Is that it if they want to participate, or is it they just show up, or just show up? So just show up on if you have any equipment that you would like to get rid of or maybe acquire. So that's all I have. Next meeting, February 13th. And unless anybody has anything else, I thank everyone for coming tonight. And we will see you on the 13th, and I will call the meeting adjourned.